wireless, and more. Please be sure to visit www.isa.org/training for more information or to register. ISA is the leading international technical society in instrumentation, systems, and automation. With 33,000 members worldwide, ISA is recognized as a leading source for training, instruction, and laboratories.
Good day, everyone, and welcome to the ISA Web Seminar, Introduction to Level Measurement. Your seminar materials include a downloadable presentation, a question and answer session, and a Zoom-link seminar survey which will be sent to your email box to complete immediately following the seminar. You earn a 1 PDH for attending. Also, as a note to attendees, this seminar will be recorded. Today's seminar is 60 minutes in length. There will be 3 10-minute question and answer sessions. As a participant, you are in a listen-only mode. You may ask questions via the Internet using your keyboard at any time during the presentation. However, the presenter may decide to wait to answer your question until the next Q&A session. If you have audio difficulties, press *0. Questions may be asked via your telephone line. Press the *1 key on your telephone keypad to ask a question. If there are no other callers on the line, the operator will announce your name and affiliation to the audience and then ask for your question. If other participants are asking questions, you will be placed into a queue until you are first in line. While in queue, you will be on listen-only mode until the operator indicates that your phone has been activated. The operator will announce your name and affiliation and then ask for your question. We will now begin today's seminar with a brief introduction of our speaker, Mr. Tim Shaw. William T. Shaw has over 30 years of experience with computer-based automation systems, including developing 3 generations of DCS systems and 2 generations of SCADA systems. Former adjunct professor in the Graduate Engineering Department of Loyola College in Baltimore. Authored books on batch process control and on SCADA cybersecurity. Currently the senior consultant for cybersecurity consulting and industrial automation cybersecurity firm. Tim periodically teaches courses for ISA and IEEE. And now Tim Shaw.
All right, thanks, Rashira. All right, hello everyone, and thank you for attending today. This is the 3rd installment on our series, and we're going to be continuing today our discussion of basic process measurements. And over the next 90 minutes, we're going to try to explain the measurement principles, the instrument application, and specifications to process conditions for level measurement. Level measurement is another one of the basic process variables that's often used in measurement and control applications. So it's rather important. In the course, our objectives today are that by the time we're done, at the completion of this lecture, you're going to be able to describe the differences between point and continuous level measurement. You'll also hopefully be able to list advantages and attributes of direct level measurement devices. You'll understand the concept of displacement measurement and the way that displacers are used both for let's call it air surface to liquid interface detection and liquid to liquid surface detection. We're also going to discuss a little bit about hydrostatic head measurement, pressure measurement, and its use in determining level. We're going to talk a little bit about the problems associated with correcting for fluid columns in making measurements based on columns of fluid and hydrostatic measurement. And we're going to talk a little bit about how to create zero elevation and suppression calculations to solve the problem of instrumentation. And in addition, we're going to talk a bit about different types of technologies that are used in level measurement, including capacitive sensors, conductive sensors, ultrasonic sensors, radar sensors. So there's a variety of different types of technologies we're going to be using, and those are for continuous measurement. And then when we talk about other types of measurement for point measurement, we'll be discussing things such as radiation sensing and rotating paddles and even gravimetric type measurement. All right, so let's begin today's discussion with part one of our lecture, and this is where we will start by talking about level and giving you an introduction to level measurement. We want to talk a bit about some of the concepts of level measurement, because when people say, what's the level in a tank, they may mean actual point measurement. In other words, has the level reached a certain level or gone beyond a certain point, or they want to know exactly what the level is, or maybe they really mean what is the material volume in the tank. There are a variety of different measurement technologies and devices we can use for making a measurement. We're going to talk about some of those, some of the type that provide a visual indication and that have been used manually and then, of course, can be adapted for automatic measurement purposes. We're going to talk about making measurement through indirect methodologies. For example, we're going to talk about the use of the principle of buoyancy as a way to make level measurements in situations where it would be very difficult to take any other kind of measurement. We also want to, of course, talk about what do we mean. So let's start simply by what do we mean when we say I've got to measure level. When somebody asks you that question, you really don't quite know what they mean at that point. Are they talking about whether a particular, let's say, fluid in this case, has reached a point in a given tank or gone beyond that point? Is that what they care about? Do they care about exactly where it is? Or if a tank might contain a couple of fluids, for example, in the storage of hydrocarbon, refined products such as gasoline, jet fuel, and such, it's very common to have water that either seeps in or is part of the process that's resulting from the refining. And storage tanks quite often end up with a certain layer of bottoms, water and other stuff, that's underneath the hydrocarbons. So you might know where the level in the tank is, but you don't really know how much of that is actually your product and how much of that is the bottom. So sometimes we want to find the interface point between two fluids, or sometimes we're talking about the actual volume. We don't really care about the level in the tank. We want to know, do we have X number of gallons or cubic feet of something? Sometimes we care about level change, so it's not so much how much our level is now, but whether we've dropped below a certain critical point or how fast our level is dropping. Maybe that's an indication of a leakage condition, or maybe it's an indication, for example, that we are producing product, consuming what's in the storage tank at a certain level. Maybe we don't care about how far something is up from the bottom of the tank, but we care how far down something is from the top of the tank, because maybe our primary concern is not to overflow a tank. And of course, for a lot of people, when they say level, what they really mean is, where exactly in the tank, vertically from the bottom, is the edge of the processed material. Now, with a liquid, that's easy to identify. With things like solids, dried materials, sands, things like this, that's a little bit more difficult to identify. But we have technologies for all of this, and we do make level measurements on processed fluids, fluidized solids, and even granular solids. So when somebody says, what's the level? What's in that tank? They may mean how far from full are we? In other words, how many more feet in this tank do we have before we reach the top? Or they may be asking how far from empty. In other words, I'm consuming what's in the tank. I don't want the tank to run dry or empty, so I'd like to know how far from the bottom of the tank. Or we may be actually asking the question, what is the volume? What is the quantity of material in the tank? And that might be something that requires knowing a combination of, first of all, the level in the tank, in other words, distance up from bottom or down from top, and then the shape of the tank, and whether there's various appurtenances butting into the tank, because a volumetric calculation may not be as simple as, doing a cylindrical volume calculation, because the tank isn't perfectly shaped. So determining how much is in the tank is quite often a little bit more difficult than just identifying the level. Well, we've been making measurements of level for a long time now. If any of you are responsible for the maintenance of your automobiles, you probably every so often have to pull the dipstick out of the oil reservoir in the bottom of your engine to find out what your oil level is. Well, a dipstick is a very traditional and ancient measuring device. I'm kind of laughing as I say that, because I still know an awful lot of tank farms and refineries where a person goes out and manually dips the tank to find out what's truly in the tank, just to verify that the instrumentation's working right. But a dipstick measurement is where we insert some type of graduated scale device. It could be a long ruler, a tape measure, or a dipstick. We insert it down into the fluid to a known point, maybe until we reach the bottom or some other stopping point, and then we pull it out and find out how much of the dipstick is coated with material. And that gives us an idea of what the volume is in the tank. And as I say, we've been using a dipstick type of measurement for an awfully long time. If any of you are avid readers of Mark Twain, then you might have figured out eventually where the name comes from. And Mark Twain is actually something that was said. It was a way that if someone was on a riverboat and you're trying to determine the level in fathoms of the water to make sure that the boat doesn't run aground, then you'd have a person out at the bow with a sounding line, which is just a long string with a lead weight at the bottom, and they would throw it over and try and find out how far down before the weight hit bottom, and then they'd yell out Mark Twain. So it was, again, essentially a dipstick, but instead of a solid thing, we're using a strip of line that, again, becomes wetted by the water or fluid. So, again, we've got a way of making a manual measurement. Well, we probably don't want to have somebody go out every day, all the time, continuously with a dipstick and measure what's in most of our tanks. So, of course, through the years, automated mechanisms have been developed to make this a process that doesn't require human intervention. And one way this is done is with a motor cable assembly. And this is actually the same thing as Mark Twain would have used, except that instead of a human lowering a weight and realizing that the tension on the line just stopped because the weight hit bottom, a motor cable assembly can be used. And with a sounding bob motor cable assembly, there's a line with a lead weight or some other type of weight, but some device at the end of this that will cause the line to pull down, and we lower the line until the tension and torque on the line changes. Basically, where the bob hits the surface and where the weight that we're feeling from the motor cable assembly changes, at that point we know that the bob has reached the surface. And if the motor assembly is encoded in such a way that it can keep track of how much line has been let out, then ostensibly we have a measurement of the distance from the motor assembly down to where the surface of the fluid in the tank is. So of course, if we know how tall the tank is, we can subtract that from the top and end up with what the vertical distance in the tank is. And a motor cable bob assembly like this is something that's been used for years in the process industry to take an occasional automated measurement. Sometimes, though, our tanks are not that large. They're smaller, and we just need to look over and get an idea of what's in them. And so something that's quite often used is the sight glass. A lot of tanks have sight glasses. I have a large coffee urn that we use for parties sometimes, and other than opening the top and burning my fingers and trying to look in, I really can't tell how much coffee is left in that urn. But the urn has a sight glass, and what does that mean? It means that there's a pipe out of the body of the urn into a vertical shaft that is actually a piece of glass piping, and the water level will seek its own level, and the coffee pot, of course, is open to the atmosphere, and the coffee maker's sight glass is open to the atmosphere. So the water or coffee level in the sight glass will be exactly at the same level as the coffee or water level inside the urn itself. So if I can see the water or coffee level in the sight glass, and I can put a little scale next to it, I can get an idea of whether my coffee urn is, full, half full, quarter full, whatever. Now, the same kind of technology can be used if you have a closed pressurized vessel. The only difference in that case, and we see this in the diagram here on the right, is that we have the tank fully sealed, and the sight glass itself continues up and then enters the top part of the tank above the fluid. Now, if we presume that this is a pressurized vessel because above the liquid we've got some kind of vapor, and that vapor based on temperature is exerting a downward pressure, well, that downward pressure is pushing down on the liquid in the vessel and equally downwards on the fluid in the column in the sight glass. So again, just as if the whole thing was vented to the atmosphere, the level in the sight glass will be the same level as the fluid in the tank. And a lot of applications such as boiler level control, sight glasses are still used, and in fact, there's technologies out there where we attach light sensors and light transmitters and clamp them on the sight glass, shall we say. We shine light through the sight glass, and if the fluid's there, the light is deflected, and if the fluid's not there, the light goes through, and we can, therefore, by looking at which sensors are detecting light, we can essentially read the sight glass without having to actually stand there and stare at it. So we can still make manual measurements or even automate the process by using sight glass technology. Now, another type of method for measuring level that's quite often been used is the use of a float and cable arrangement. Now, this diagram is not exactly how it ever is built, but it gives you the principles. The notion in a cable float arrangement is that somewhere up in the top of a tank, above the fluid level, above the highest fluid level, we have a pulley. And over that pulley, we suspend a float and a weight. And the float should be slightly heavier than the weight, but designed such that, for example, in this drawing, that it's hollow. So that even though the float is heavier than the weight, when the float drops down and hits the surface of the liquid in the tank, the buoyancy of the float counteracts its weight, and it goes no further into the fluid. And so it sort of sits there floating on top of the fluid, and as the fluid level goes up or down, the float will rise up and down, counterbalanced by the weight, and the pulley has a pointer on it. So as the fluid level goes up and down, the float goes up and down, which pulls the cable, which causes the pointer to turn left or right, indicating the level in the tank. Well, that's the basic principle of a float cable arrangement. In reality, there are designs that use this concept, but are not exactly built this way. Now, one of the problems that you have with a float cable arrangement, of course, is that very few tanks filled with liquids are going to have a float surface that's stable. Whether it's because it's a very large tank and therefore there's just constant wave action as waves just bounce around, or because the tank is in operation and therefore I've got liquid pouring into the tank or being drawn from the tank, or maybe I even have to agitate the fluid in the tank and have some kind of mixer. There is the possibility that a float system will be bouncing around because of this and not give me an accurate, stable measurement. So it's also quite often to make use of a stilling well. We talked a minute or two ago about a sight glass, and I said the sight glass is where we tap off of the tank and come out to a vertical column. And that would allow us to take a look at the level, because the level in this outside column will be the same as in the tank itself. Well, we can make use of this principle. We can attach a stilling well to a tank, and we can put our flow tape system on the stilling well. And the stilling well, because it is coming off, as you can see in this case, the bottom of the tank, we don't have the same problem with surface agitation. Now again, this drawing's a bit simplistic. In most cases, you'll see that a stilling well is actually a pipe inserted into the tank itself, somewhere off to the side, but in the tank. It's usually not built as a separate entity. But the concept of having a separate protected vertical column where the fluid can only come in from the bottom, and thus we avoid the fluid surface agitation problem, that is common to the way we make use of stilling wells. So if you're going to use a flow tape system, you probably will use some type of stilling well to make sure you can get an accurate measurement. So in real life, what does this flow tape system really look like? Well, here we have a drawing that is actually quite realistic. I've seen a lot of tank farms where as you walk by a tank, on the side of the tank, painted up the side of the tank, is a scale. And there's a sliding pointer, something big and obvious to see, that slides up and down the scale, and it's driven up and down by a set of wires that go up the side of the tank through some type of piping arrangement and down into the tank to where the float is. And there are quite often guide wires inside the tank that make sure the float isn't bobbing all over the place. But essentially, this is this kind of scheme you're just talking about, this float and cable arrangement. I've got a float in the tank that is guided by some guide wires, but as it goes up and down, the cable from the float goes up through some pulleys, around some piping, and then down to the outside, where it is kept tense by this pointer, which is usually not just a pointer but also the counterweight. So again, as the float goes up and down, the pointer rises and falls, and the scale gives me an idea of what's in the tank. Of course, the thing you've got to keep in mind is that it's an inverse measurement. As the level goes up, the pointer goes down. So the pointer at the bottom of the tank indicates a full tank. The pointer at the top of the tank indicates an empty tank. The good news is that instead of having to run around and read the pointers on the sides of the tanks, these days the same kind of companies that make flow tape systems can mount an encoder on the side of the tank, so that an encoder can be thought of as sort of a reel with a spring attachment on it, so that as the float goes up and down, this reel reels in and lets out the line. and the line has some encoding on it. Usually in the case of a tape float system, it's usually some punch-coded punch hole values that allow me to count sort of how many inches of tape go in and back out. And this can be converted to an electrical signal, and I can get a 4 to 20 milliamp signal sent back to a control room somewhere. Now, in some cases, I can't really get into my tank and have it vented to the atmosphere. I need to make a measurement in a sealed environment. And one of the things we can use in those cases is we can make use of the principle of buoyancy. Buoyancy was discovered a long time ago. The ancient Greeks had it. In fact, we've got a wonderful quotation that starts with Eureka that goes on to a Greek philosopher sitting in the bathtub and figuring out how to tell whether a gold crown was gold-plated or solid gold. But we won't get into that. Let's mention a simple fact, that if you take an object and submerge it into a liquid and you take the volume of liquid that it displaces and you weigh it, you will discover that the hanging weight of that object is reduced by the weight of the liquid it displaces. So if I have a cylinder, as this diagram shows, a hollow cylinder, and it's hanging from a weight measurement device, a scale of some type, and here on the left-hand side I'm showing a displacer, a hollow metal cylinder hanging in a tank, and there's water at the bottom of the tank, but the displacer is above it, and we see that this displacer hanging in air weighs 15.5 pounds. Now, as the water level in the tank rises, more and more of the displacer is in the water, and it's displacing its own volume of water, and that water that's being displaced is pushing back against the displacer and essentially pushing it upward, and therefore making its hanging weight seem less and less. And in the middle part of the diagram here, we can see that our water level has gone up halfway into the tank, and our displacer now seems to have a hanging weight of 14.8 pounds instead of 15.8 pounds. Its weight has reduced by 1 pound. Well, obviously its weight hasn't gone down. What's happened is that the pulling downward force of its weight is being counteracted by the pushing upward weight of the liquid that it has displaced, and therefore its apparent weight is 14.8 pounds. And in the final diagram, the displacer now is shall we say, fully submerged, or at least submerged to the maximum level of liquid that we're going to allow in the tank. So the water level is now up to 14 inches in the tank, and the displacer's hanging weight is now down to 13.8 pounds. So what have we seen here? What we've seen is that we can make a level measurement. We can tell that the level of water in this tank is between 0 inches and 14 inches based on the weight that we're measuring varying from 15.8 pounds to 13.8 pounds. So as the water level goes up, the hanging weight goes down. We have a 2 pound, 15, 16, 13, 14, 15, right. We got a 2 pound weight difference that is an indicator of a 14-inch difference in the level in the tank. So by watching the differential in the weight, the hanging weight of this displacer, we can make an inferential determination of the level in the tank. Now, it may not be clear, but when the water level of the tank is all the way down to the bottom, you'd sit there saying, well, the displacer is just hanging there. Yes, it is, but it's actually not just hanging there in vacuum. It's hanging there in air. So what we're really doing is we're measuring, and believe it or not, air has the same kind of buoyancy effect as any other fluid or liquid. It's just extremely small. So when we look at the weight of this displacer, we're actually measuring the weight of the displacer fully submerged in air all the way up to where it's now fully submerged in water instead of air. Well, if we keep the same concept in mind, we can make an interesting use of a displacer. What if what I'm trying to measure is not so much what's in the tank, but what's in the bottom of the tank? So let's go back to the example of a large storage tank at a refinery, and the tank is holding gasoline or kerosene. Right, but over time, water seeps in and starts filling up the tank, or comes in, as water that's actually in the refined products due to the refining. And so eventually, water collects in my tank and slowly builds up. And I want to know not the level of the overall liquids in the tank, but how much of that is water. Right, so my tank is, well, in this case, it's a 14-inch deep tank. But how much of that is refined product and how much of it is water? Well, we'll go to the same concept here. the first diagram on the left-hand side, we're showing the water level all the way down at the bottom, so we have no water in the tank. The tank, though, is fully filled with a distillate. So my displacer is hanging there, floating, shall we say, or hanging in the distillate. So it doesn't have the same weight. When it was hanging in midair, it weighed 15.8 pounds. Now it's hanging fully submerged in distillate, and it only weighs 1.4 pounds, right, because it's fully submerged. But as the water level in the tank rises, again, the water will be pushing against the displacer, and the density of water is different from the density of the distillate. Obviously, its density is greater, which is why it's sunk down below. But as the water level rises, we will again see the weight of the displacer change. So let's just cut to the chase. When the water level is all the way up to 14 inches, meaning pretty much the tank is full of nothing but water, the hanging weight for the displacer is now 1 pound. When there was no water, it was 1.4 pounds. So now we can measure the water in the bottom of the tank using a displacer that's put down there in the bottom of the tank to know the level of water in the tank from no water all the way up to 14 inches by seeing the weight of the displacer change between 1.4 pounds and 1.0 pounds. So displacement can be used to not just identify the interface between a liquid and the atmosphere, but it can be used to identify the interface between two different liquids that have different fluid densities. So that's another very valuable use of displacer measurement technology. All right, so we started this first section by talking about level. What do we mean by it? Are we talking about a measurement from top or bottom, or how much is in the tank? Are we talking about knowing whether a level is above or below a certain point, or exactly what the level is? We've talked about a variety of different measurement types of devices: dipsticks, steel tape, float systems, and then, you know, the use of a principle of buoyancy to use with displacer technologies. So we've covered a variety of different topics, and at this point we're at the end of section number 1. So if I could please, Rashira, let me turn this back over to you to see if we've got questions.
Thank you. If you would like to ask a question, press star 1 on your telephone keypad to ask a question. If there are no other callers in line, the operator will announce your name and affiliation to the audience and then ask for your question. If other participants are asking questions, you will be placed into a queue until you are first in line. While in queue, you will be on a listen-only mode until the operator indicates that your phone has been activated. The operator will announce your name and affiliation and then ask your question. Again, if you would like to ask a question, press star, then the number 1 on your telephone keypad. Again, star 1 to ask a question. There are no questions at this time.
All right. Well, thanks, Rashira. All right, everybody, let's go on then to the next section, section number 2. Do keep in mind, though, that if you come up with a question later on, you don't have to restrict yourself to just section 2 or section 3. We'll take any question. So, section 2, part 2. We want to now talk about a different way of making level measurement. And this is kind of an indirect way. And we're talking about measuring level through the use of pressure. Turns out that if you have a column of liquid, that liquid has a certain weight per unit volume, and that weight presses down and creates a force. And we can measure that force in terms of pressure. And pressure is a force over an area. We usually measure it in terms of things like pounds per square inch. Well, a column of fluid will generate a pressure, and the higher or lower the column, the pressure will change. So therefore, we can use this concept of measuring what's called head pressure to get an idea of a level in a tank. And in fact, we use the term hydrostatic measurement to describe the use of pressure generated by a column of fluid as a way of generating a measurement of level in a tank. And the use of hydrostatic pressure is different whether it's an open tank, open to the atmosphere, or closed with some pressure above it, but the concept still works. So we're going to talk a little bit about how to use hydrostatic pressure for measurement. We're going to talk about a variation on the same principle using a dip tube or bubbler. And we'll again finish up this with some questions. So, basic principles. If we were to take a cubic foot of pure water at 60 degrees Fahrenheit and somehow set it onto a scale and make it, measure its weight, we would find that that water weighs 62.4 pounds. Okay? Now, that water's weight is in fact a force, because weight is actually mass times gravitational acceleration, and that's what we call a force. So when we say something weighs something, what we really mean is the gravitational acceleration of its mass is producing that force downward. Now, if it's a cubic foot of water, that means that the surface area that we're pressing down on is a foot by a foot, or 144 square inches, right? So if we divide that out, we find out that the pressure down on 1 cubic inch of bottom area, rather than the whole thing, is 0.433 pounds. So in other words, the downward force or pressure of a column of water 1 foot high on a single square inch of surface is 0.433 pounds. That's an important number because we use that number in a lot of cases for calculation of our level in tanks. Of course, if we're in Europe, we use a slightly different thing. We're going to be talking about 0.03 kilograms of force per cubic centimeter, or square centimeter, but there are conversions that go back and forth. But that's the basic principle. The column of fluid presses down on a given surface area, and if we can measure that pressure, we can determine the height of the column. In fact, we've been using that concept for years. One of the most early type of pressure measurement devices was something called a manometer. And a manometer basically is a tank of liquid with a vent on top into which we can push a pressure, so we can put a gas pressure or something else into the top of this tank. And the tank is filled with liquid, which is then pushed out into a vertical column, again a sight glass. And based on the pressure pushing into this reservoir of fluid, we will push this fluid to a greater and greater height, h. Now, the issue here is going to be a couple of things. First of all, what is the fluid? We've already said that water, which we declare as having a standard density of 1, specific gravity of 1, that's our reference point. We said that water pushes down at a 0.433 pounds per square inch per foot of elevation. So if we can measure the feet of elevation of a column of water, we know how much pressure is pushing against it. If we're not using water, if we're using some other fluid, let's say mercury or oil or something else, then we have to know what the density of that liquid is relative to water. If it's heavier than water, then we would expect for the same pressure to have a shorter height of the column. If its density is less than water, in other words, it's lighter, we'd expect the column to be pushed even higher for the same pressure. We can use this concept to make a measurement calculation of the height of liquid in a tank. Because remember, as we said, if we go back to the sight glass example, if we take a tap off the tank at the bottom of the tank and bring it to a vertical column of some type, sight glass, for example, the water level in that column is going to be exactly the same as the water level in the tank. So if we can measure the pressure down at the bottom of that column, which is in fact the pressure at the bottom of the tank, we can get an idea of how high the fluid level is in the tank. But again, we have to correct. Now, in this diagram here, we do have an equation. If you look at the tank down at the bottom on the left, there's an equation that says that the pressure on the bottom of the tank, so if I were to tap at the very bottom of the tank and take a pressure measurement there, the pressure in pounds per square inch is going to be equal to 0.433 times the specific gravity of the liquid, which if it's water is 1, times the height of the liquid in feet. So if I had 1 foot of water in this tank, I would make a measurement of 0.433 pounds per square inch, because 1 foot of water gives me that. If I've got something other than water, I need to know its specific gravity. If the height is other than 1 foot, then my number is going to go up or down. But the point is, I can take a pressure and I can calculate it from the height. So, of course, I can do the opposite. If I have the height, I can calculate, if I have the height, I can calculate the pressure. But if I have the pressure, I can, in reverse, calculate the height. And that's what hydrostatic tank aging is all about. We take the pressure at the bottom of the tank and use that, knowing the specific gravity of the fluid, to compute what the height of the fluid in the tank must be. So, in this diagram, we have an open-to-air tank And we do have to remember something. The tank is not in outer space. We don't have vacuum. There is atmosphere. And trust me, if you've got a mile of air piled on top of you, it's pushing down. And in fact, the standard that we use is that at sea level, the standard pressure of the atmosphere is treated as being 14.696 pounds per square inch. So we've already got a downward pressure. Forgetting the liquid in the tank, we've already got a downward pressure of 14.69 or 14.7 pounds per square inch because of atmosphere. Now we put liquid in the tank, and that pressure downward is going to be added to the pressure downward of the liquid itself. So we've already said that if we've got a column of liquid in the tank that's h feet high, h times 0.433 times the specific gravity, which in this case is 1.2, will tell us the pressure. We'll read at the bottom, and that pressure in this case is being shown as 6.5 psi. Well, if you think about it, how can that be 6.5 psi? I've already told you that the atmosphere is pressing down with 14.69 psi. So it's got to at least be that, right? Because we can't have less than atmospheric pressure. Well, here's where we have to talk about how we take pressure measurements. That instrument that we show hanging off the bottom of the tank, that PI, that pressure indicator, that is probably a pressure differential transmitter. In other words, it is a device that is not measuring the absolute pressure. It's measuring the pressure difference between one side and the other side. And we're not showing the other side, but if you were to take that PI device and draw a pipe out from the right side and just let it hanging in air, you'd actually have a much more realistic diagram here. So in fact, this PI indicator device has one of its sides open to the atmosphere. Because it's open to the atmosphere, that side is feeling atmospheric pressure at 14.69 psi. So the pressure that it's feeling from its open tap on the right side is canceling out the pressure that the atmosphere is placing on the measurement it's taking on the left side, and therefore the only pressure we're really measuring is that which is in the tank. Okay, which is in the tank. So if we use differential pressure measurement and we open one side of the pressure measurement device to the atmosphere, then it will correct for the fact that the atmospheric pressure on the open tank is this 14.69 psi. So we've got to be able to correct for that. All right. We also have to correct for something else. When we talk about a column of fluid, we're not just talking about the fluid in the tank. Let's say my pressure measurement device is not mounted right there on the tank itself. I'm going to put my differential pressure sensor 50 feet away from the tank, and I'm going to run a pipe, a small pipe, an impulse line, from the tap off at the bottom of the tank over to that pressure transmitter. And in this case, now we are showing both the left and right side, or the high and low side. So this level transmitter is really a differential pressure device, and it's looking at the pressure on the low side, which is atmospheric pressure, and the pressure on the high side, which is both atmospheric pressure and the pressure generated by the column of fluid in the tank, and it's feeling the difference. And we just said a minute ago that if we use this kind of scheme, we can ignore the atmospheric pressure because it balances out. So we're going to ignore it for the moment. But what is the pressure that's being felt on the high side of this pressure transmitter? Well, it's certainly going to be the amount of fluid on this diagram called B. So we've got our tap-off point, and the fluid is B inches above that tap-off point. So we've got certainly B inches of fluid. But that's not really what we have, because this transmitter device is not only located away from the tank, but it's also C inches, or 24 inches, down below the level of the tap-off B. So the point in fact is the liquid column that's attached to the high side here is a column of fluid that's B plus C, in other words, the fluid in this impulse line, of elevation. So actually my starting point for measurement here is not 0, but C. So even if the tank were all the way down to where the fluid just dropped right down to where my tap-off point is, I still have 24 inches, or this C value of fluid in this impulse line that's pressing against the pressure transmitter. So I've got to correct for that. That's my 0 value. So in other words, even when the tank's essentially empty, I'm still measuring 24 inches of fluid in the tank, so I've got to correct for that. I've got to subtract that off, or zero the calculation. So when we talk about taking a measurement, and in this case where we use a fluid-filled line, an impulse line, to leave the tank and bring the fluid over to the level transmitter itself, we've got to remember that that line, that impulse line, is also filled with fluid. And that fluid is going to press down and be providing a bit of pressure itself. So in this particular case, we've got the problem of zero suppression. We've got to correct for certainly C inches or 24 inches of fluid. But now we should also notice that on this tank, we've decided that we don't want the level to go below what's shown as the minimum level. And the minimum level is 10 inches or B above the tap point. So point in fact, we would want the level indicator to show that we are at zero usable level, or 0% usable level of the tank, which doesn't mean it's empty, but we're at the minimum level when we are reading 34 inches of pressure, because we've got 10 inches above the tap and then 24 inches down to the pressure measurement device. So my zero suppression has to correct for 34 inches of fluid column. That's what I want. So when I measure actually 34 inches of pressure, that should be considered 0% tank level. Now when I measure 24 plus 10 plus 120 inches, in other words, we're up at the maximum level in the tank, that pressure is what I want to be indicated as 100% in my tank. So my tank transmitter, my level transmitter, is going to be zeroed out to show 0% usable tank when I am measuring a tank level pressure that's equal to 34 inches of fluid. And it's going to show an indication of 100% of the usable value of the tank when I'm measuring 120 plus 10 plus 24 inches of fluid in the tank. Okay, that much pressure. So that's what we mean when we talk about zero suppression in the tank, and also how we have to think about calibrating the pressure transmitter to give us accurate measurement. Okay, so we don't want to think there's something in the tank where there isn't. Now, that's fine when we've got a tank that's vented to the atmosphere. Now, what about a tank that is, in fact, totally sealed and closed and pressurized, where we have something where there's going to be vapor exerting a pressure on the fluid in the tank? How do we read that? How do we correct for that? Well, we can use the same situation. Now, that low side leg of the level transmitter device, instead of being vented to the atmosphere, we pipe it up and bring it over and plug it back into the tank above the maximum fluid level. So that leg is called a dry leg, because in theory it has nothing in it except, the gas, shall we say, whatever the gas is that's above the liquid level in the tank. So as long as that leg is dry and empty, then whatever the pressure that is being generated by the vapor in the tank that's pushing down against the fluid in the tank, that same pressure is going through that dry leg and pressing against the side of the pressure transmitter that's doing the differential. So again, this arrangement corrects for the pressure in the vessel, but we still have the problem of zero suppression. So even though we've corrected for the effects of pressure, just like we correct for the effects of atmospheric pressure, we still have to zero correct. We still have a transmitter that is tapped in at 10 inches below the minimum level of the fluid in the tank and located 24 inches below that tap. So in other words, that fluid in the high side leg will always be a minimum of 34 inches of fluid. So we've still got the problem of zero suppression, but we've just corrected with a dry leg connection to the top of the tank. We've corrected for the problem of the pressure in the tank. And that sounds great, but there's another problem, and that is we refer to that leg on the right-hand side as a dry leg, and that's great. But the problem with dry legs is they don't stay dry. Typically in a pressurized tank like this, that vapor above the fluid quite often is some type of condensing liquid. For example, let's just assume the tank has water. It's a boiler, right? So what's above the fluid level is steam. Well, that means that steam is going out through that tap up top into the wet leg, and what happens with steam? If we put steam into that wet leg, eventually it cools down, and what happens? the dry leg. That dry leg eventually is no longer a dry leg because water condenses and eventually fills it up. So what is going to eventually happen in many cases, if we have a condensing fluid, a condensing vapor above the liquid, is that the ostensible dry leg now ends up filled with fluid. So now what's our situation? So I've got a leg here that's supposed to be dry, but it's not dry anymore. It's filled with liquid. And in fact, the liquid is all the way up the wet leg, what's now a wet leg, not a dry leg anymore. And we know that that is a column of fluid that is 140 plus 24 inches in height, because we are 24 inches of elevation below the tap, and we allow the tank level to go up to the maximum level. That's great, but what was a dry leg tap is above the maximum level. So it's actually 140 inches up. So we now have a column of fluid that is 164 inches, and it's there all the time. It doesn't go up or down. In other words, the legs fill up with fluid, and now we have a wet leg that actually is a column of fluid that would be greater ever than the column of fluid in the tank. In other words, the tank's never allowed to go above the maximum level, and that's 20 inches below the tap point where we put the upper tap that was supposed to be a dry leg. So what we now have is a situation where actually things are reversed. We say on the transmitter here that the high side and low side actually switch, because now the pressure on what is now a wet leg is actually a high pressure, and what we're looking at is the difference between it and the level in the tank. So as the tank level goes up, the difference between the high side and low side goes down, not up, it goes down, because the pressures are getting closer to each other, and once the level in the tank is all the way up to the maximum level, the difference between the two sides of the tank are going to be just 20 inches of fluid pressure. So here we've got a case where the wet leg, or where the dry leg is no longer a dry leg, it becomes a wet leg. And we basically have to switch the transmitter around and think of what is now a wet leg as our high pressure side. Now, actually, in most applications, recognizing that this is going to happen, we have two choices. We either put some kind of a manual valve that can be used occasionally to drain fluid that's building up in the wet leg, in the leg that should be a dry leg that's becoming a wet leg, or we just agree that it's going to become a wet leg eventually anyway. If we don't come out and spill the fluid out occasionally, it's going to screw up. What if we're dealing with a fluid where we just can't open the valve and let it go because it's something toxic? Heck with it. So instead what we'll do is we'll intentionally fill that high leg with fluid and just treat it as our high leg with our high pressure, and we'll flip our transmitter around and we'll look at the pressure difference between the high column of fluid, which is this filled leg, and the actual fluid level in the tank itself. So if we have a closed tank where we have the possibility of the dry leg becoming wet, then we just fix the problem by making it wet. And so there's fluid in both legs, but the fluid column in the upper leg is stationary, and it's always at the maximum value, and the fluid in the tank goes up and down, and as it goes down, the difference becomes greater. As the fluid level in the tank goes up, it becomes less. So it's inverse acting. But again, we can correct for all this, and we can calibrate our instruments appropriately and still get an accurate measurement of what's in the tank. Now, another way of measuring what's in a tank is again, working off the basis that we know that the deeper the fluid is, or higher the level of fluid is, the greater the pressure. So if I stick a pipe down into a fluid and blow into that pipe, no air will come out the bottom of that pipe until I'm blowing into the pipe hard enough such that my air pressure into the pipe exceeds the fluid pressure that's trying to push back up into the pipe. In other words, fluid wants to enter the pipe and go up to the level that's in the tank. For me to blow that fluid down, out, and keep it out, I've got to blow air into that pipe and continue blowing air into that pipe, letting it escape out the bottom end. But the pressure into that pipe has to be at least as great as the pressure level down at the bottom of the pipe. So in other words, at the bottom of this bubbler pipe, there's a liquid pressure based on the level, and the airflow in has to match that. And we can use that scheme. In fact, bubbler systems are a very common way of measuring the level when we've got something that's really ooky and messy. For example, if you've got high viscosity fluids or something that's dirty or horrifying, where a typical measurement device would get jimmied up or gooed up or whatever, because an air bubbler system just relies on pushing the fluid out of the pipe and keeping it out by a constant flow of air, it's to a degree self-cleaning. Well, if we make a measurement of that back pressure, in other words, the amount of air pressure we have to push in to keep the fluid out of the pipe, that pressure is in fact proportional to the level of fluid in the tank. And if we make a measurement of that, and here we show an indication of that where we got a level transmitter that again is a differential pressure measurement. It's measuring the pressure of atmosphere on the low side, because again this is an open tank, against the pressure that has to be pushed down through the pipe to keep the bubbler from having fluid in it. That pressure differential gives me exactly the same kind of capability as any other hydrostatic, and I can compute the level in the tank from that. So a bubbler system is another commonly used mechanism, especially in dirty, ooky, crappy applications where the fluid here isn't something as nice as water. All right, let's take a look at an actual typical level measurement application. If you're in the water waste industry or just happen to like to drink water and be able to turn your faucet on, then it's probably been something you've noticed that in your neighborhood somewhere where every so often you see these big above ground water storage tanks. They may be the golf ball shaped tanks or an older tank that looks like this thing, but these tanks hold water up above ground level at a certain elevation in order to generate a certain pressure so that the water can push its way all through all the pipes and into your home and up to your second floor or third floor. So the question here would be, if I want to know the level in this tank up here above ground, can I determine that level down here at ground level by taking a pressure measurement on this pipe down at the base of the tank? Well, we've got a variety of numbers here. All right, we know that the tank itself, at the bottom of the tank, is 70 feet above ground. We also know that our measurement device here is 5 feet above ground. So when there's nothing at all in the tank, when the tank is empty, presuming that we don't, suck the water out of the pipe that goes up to the tank, we know that we will have a 70 minus 5 or a 65-foot high column of water when the tank is absolutely empty. When the tank is full, we know that we'll have 35 feet more than that. So we'll go all the way up to what is it? It's 70 plus 35. You do the math. But so our tank level is going to vary up and down by 35 feet. What we're going to measure at ground level, or 5 feet above ground level, shall we say, will be a fluid column of 65 feet up to 65 plus 35 feet. Right? So we're going to be measuring that pressure differential. Since this is water, we already know that height of a column of water in feet is equal to or proportional to the pressure that we're measuring and the specific gravity of the fluid, which is, of course, 1 because it's water. So if we can take a pressure measurement, we can actually compute the height of the tank. Right? So the height of the tank in this particular case is going to be the pressure we measure divided by 0.433 times 1, or it's going to be a pressure measurement of 40 psi over 0.433, or it's going to tell us that we're reading a column height of 92.378 feet of water. Right? Now that's feet of water up to the tank and where the level is in the tank. So we would know that we're 92 feet above, 5 feet above ground, or we're 97 feet up from ground level. So since the tank is 70 feet, we subtract 92 from that, and what we find out is that the level in the tank is 27.38 feet of water. Okay? In other words, it's about 78.22% full. And we can do that all by just having a pressure measurement down near ground level and knowing that that pressure is being taken 5 feet above and that we've got a 70-foot minus 5-foot column of water. Right? So we can do the math and come up with that and do the calculation and find out that, in fact, we have the distance minus the level in the tank, and we come up with the fact that we've got, as I said, 27.28 feet of water in the tank itself. Okay? So this is where being able to do hydrostatic measurement is handy. It might be very difficult to get up and put some kind of level measurement device up in the tank, but we can certainly take a pressure measurement down near the ground. All right, so hydrostatic pressure measurement. It works off of the basic principle that a column of fluid exerts a downward pressure or force, and that pressure or force is going to be proportional to the height of the column and the specific gravity or the weight per unit volume of the fluid. So a heavier fluid is going to push down and have a greater pressure than a lighter fluid. So a foot column of water will give me a certain pressure. The same foot column of mercury will give me a much greater pressure, and the same foot column of, jet fuel will give me a lesser pressure because it's got less density. So that's the finish up for our discussion, and we've talked about a couple ways of doing hydrostatic pressure measurement, including using an indirect methodology like that dip tube or the bubbler system. So at this point, we're done with section number 2. Here, if I could, let me turn it back to you to see if there's questions.
Again, press star 1 on your telephone keypad to ask a question. If there are no other callers in line, the operator will announce your name and affiliation to the audience and then ask for your question. If other participants are asking questions, you will be placed into a queue until you're first in line. While in queue, we will be on a listen-only mode until the operator indicates that your phone has been activated. The operator will announce your first and last name and affiliation and then ask for your question. Again, to ask questions, press star, then the number 1. And there are no questions at this time.
All right. Thanks, Sheriff. All right. Well, in that case, let's go ahead and jump on to our third and final section today. So far, we've been talking about a variety of different direct and indirect measurement techniques. Many of the ones we discussed earlier were mechanical in nature. We just finished talking about how to compute and calculate level indirectly using pressure. In this third section, let's talk about actually the way we can use electrical measurement devices, things whose electrical properties change and vary according to level as a way of measuring, because these are also very commonly used devices. We're going to take a look at sensors that use capacitance, conductance, and resistance changes to indicate level. We're also going to look at some more high-tech devices. We're talking a little bit at the end here about using ultrasonic devices and even radar sensor devices to make level measurements. Now, a capacitor, if you're an electrical engineer, a capacitor is a pair of conductors. Quite often we just show a couple of metal plates separated from each other by an insulator, something that doesn't conduct electricity. This could be oil, it could be air. And we put a charge across these two plates, and their ability to hold and store a certain amount of electrical energy is directly proportional to what's called the capacitance. So a couple of metal things close to each other, isolated by a conductor, forms a capacitor. So in fact, if I have a metal tank and it is filled with in one case, a non-conductive fluid, let's say a hydrocarbon, and I can insert down into that tank a metal rod, which of course has to be insulated from touching the tank, then the rod and the body of the tank are two separate metal surfaces, and they form a capacitor. And if I make a measurement, an electrical measurement across them, that capacitance is something I can measure. Well, as the fluid level in a tank goes up and down, especially in this case here we're talking about a non-conductive fluid, it actually changes the measurable capacitance of this two-conductor, capacitor we've created. So by measuring the capacitance that I'm getting between the probe metal and between the wall metal of the tank, I can make an inferential calculation of the level in the tank. And a capacitive probe level measurement device is a very typical thing we use these days. Now, of course, if you have a non-metallic tank, it becomes a little more tricky. In that case, typically you insert tube probes. If you have a fluid in the tank that is conductive, then actually what happens is you take your probe and you coat it with something. For example, totally coat it with a plastic and stick it down in. So again, you've got insulation. But in all of those different cases, there are solutions, and there are vendors out there that have the ability to pretty much deal with a wide range of different applications. And capacitive level measurement is a very well proven and commonly used technology. There are other types of technologies that work on similar properties. One, a very simple one, is conductivity. If I've got a fluid that, in fact, is conductive, then I can put in a series of metal probes down into the tank. Of course, they have to be insulated from the tank at different levels, and I can measure the resistance between those various probes. And as the fluid level rises or drops in the tank, I can determine how high the level is, knowing the lengths of my probes, because as, for example, in this case, as the fluid level reaches up to where the C probe and the on probe are both covered, I'll measure a resistance between the two of those that has just dropped because the fluid's conductive. When the fluid finally gets up to the third probe, then I'll measure between C and the off probe that there's now a drop in resistance and conductance. And by making the measurement between these various probes and determining how many of these probes I want to stick into the tank, I can make point measurements. Now, we do want to make an indication here. We're talking about point measurements. In other words, as the level goes up and down, we're not really trying to measure the change in level. What we're merely trying to do is make what's called a point measurement. So once the level reaches the on probe, anywhere from there upwards, we can see that there is conductance between the C probe and the on probe. We can't tell you what the exact level is. All we can tell you is that the level has at least reached on. Once it reaches the off probe, we can measure that and tell you that the fluid level has at least reached the off level. So, of course, it's above the on level, but it's at least reached the off level. How far above that, we don't know. If you really need to know, then you either need to use some type of continuous level measurement or you need to stick a few more probes in. But in many cases, in certain types of tanks and applications, we don't really care what the absolute level in the tank is. We care if the tank drops below a certain level. We care if the tank is getting above a certain level, but in between we probably don't care. So in that case, using conductivity sensors like this with these simple probes might be a perfectly applicable way of measuring the level in the tank. But again, those are point measurements. Another way that we can make a measurement of level in the tank is by using a resistive tape level sensor. The best way to think about this is that I've got a long pipe made out of soft, flexible plastic that is inflated by a little bit of air pressure inside of this plastic tube, but that the inflation pressure is very small, and that if you were to press against it, the tube would crush down and collapse. And I've got a set of wire that runs down one side of the tube and then down the other side of the tube. And that wire has a certain resistance. And in fact, it's a helically wound resistor. Now, if we submerge this tape into a fluid, what's going to happen is that as the fluid level goes up and up and up, we submerge the tape by a certain amount. Once the tape has been submerged by a certain amount, the pressure generated by that certain amount of fluid will cause the tape to collapse, causing the two conductors to touch and short out. So if the tank's totally empty, then this resistive strip is not touching anywhere, and I have the maximum resistance. As the fluid level in the tank goes up and up and up, more and more of this tape is crushed or pressed in, and the resistive part of it touches and is shorted out, and so the resistance drops lower and lower and lower. So I can calibrate for this. I can put this tape into my tank, raise the fluid level up and down, and make a measurement, and by measuring the resistance through this wire, I can get a rough idea of the tank level. I say rough idea because obviously you have to have a certain amount of increasing tank level before the next bit of tape will short out, so this isn't a high precision measurement, but it does give you more of a continuous indication, for example, than the prior thing where we just used probes of a certain distance in. So we do have the ability to measure resistance based on using a technique like this. Now, another type of electrical measurement that's a little more active than this, and that doesn't use contact, is to use ultrasonics. You may or may not be familiar with the use of ultrasonics. You probably actually use them all the time, whether you know it or not. If you've ever been pulled over by a police officer who pointed a gun at you and came up and said you were speeding, he may have been using ultrasonic measuring. He may have been using the speed difference generated by a pulse sent towards you and bouncing off of you to measure a frequency difference which is called the Doppler effect. The point is, ultrasonics are nothing more than sound waves, and we can generate a sound wave and point it towards something, and if it strikes that something, it should bounce back to us. So it's a reflective type technology. Ultrasonic measurement essentially consists of generating a sound pulse and waiting to hear it come back. Now, if you've ever been in places like the Grand Canyon or places where you're, in a valley and you've got a hill nearby and you yell, right? And you yell, hello! And a second later you hear, hello! Well, you understand the concept. The speed of sound through a gas or fluid is not fixed. It's going to depend on the density and the temperatures and such, but it can be corrected for. If we make a sound pulse and send it through liquid or gas, and it hits a surface, it's going to bounce back. So if we start a timer going from when we transmit the sound pulse and count when we hear the echo, so we hear our hello back, by counting precisely the time difference, we can compute the distance from our transmitter device to the surface we're measuring. So it's a distance measurement. In fact, if you used to have an old Kodak camera years ago, or Polaroid camera years ago, they used ultrasonic sound bursts to automatically focus the camera. Well, we use the same type of technology. We can send a sound burst downwards from the top of a tank into and through the tank, and the sound burst can hit the fluid or solid material and bounce back. And if we're timing it appropriately, based on the distance, we can calculate what the, or based on the time, we can calculate distance. Also, the speed of sound through air is proportional to the air temperature, so quite often when we use ultrasonic measurement, we may also be making a temperature measurement at the same time, so we can correct for that speed differential. So in a lot of cases, we'll use ultrasonics to take a measurement, which is really a measurement of distance from the top of the tank down to the surface we're looking for. So we put an ultrasonic transducer at the top of the tank, and it will, on a regular basis, send out a sound pulse and then listen and time and count how long it takes for the sound pulse to come back. Now, there are a variety of things you have to consider when you use ultrasonics. For example, depending on what's in the tank, if you have a lot of suspended particulates and dust in the tank, that can actually cause false readings. Or if the tank has a lot of appurtenances sticking into the tank on the sides, and you haven't aimed and focused the ultrasonic transceiver appropriately, you might actually hear a reflection off of one of these appurtenances or obstructions and think that that's the level versus the actual level. But if you follow the manufacturer's instructions right and set things up appropriately, ultrasonic measurement can be used quite successfully in a lot of applications. Now, ultrasonics, as I said, are affected by temperature. They can be affected also by particulates and vapor pressure and other things. So they're not right for everything, but they are commonly used. But a variation on this same kind of concept of measuring distance down from the top of the tank by timing something is the use of radar. And in fact, radar gauge technology was invented years ago and has been used on things like tank ships, large ocean-going tankers for years to make level measurements. But the costs and technologies have evolved significantly now to where it's very reasonable to consider using radar technology in a lot of other applications. Radar technology can be non-invasive in some cases. And what do we mean by that? Well, if we have a tank that is invisible or transparent, shall we say, to radar, for example, the tank is not metallic, it's made out of plastic or something, then we can mount our radar transmitter outside the tank and never have to be inside the tank at all. On the other hand, if we have a metal tank, we can sometimes mount a porthole, shall we say, in the top of the tank, something that has a very strong glass or some other type of transparent material, again, something that radar doesn't really see and can go through, so we can still keep the radar transmitter outside the tank. So if we're dealing with caustic materials or something where we really just don't want to put a penetration into the tank because of tank pressure, for example, then sometimes we can use a non-invasive radar transmitter. Now, radar, again, is a situation where we send a pulse down and we time it, and when it reflects, we can measure the timing. Now, radar and sound are a little bit different in their properties. Radar has a much smaller wavelength, and so sometimes with a radar system, we can actually get some interesting things to happen. First of all, radar tends to be less affected by temperature variations in atmosphere and particulates. There are certain things, though, that radar doesn't work well in. It turns out that there's certain molecular compounds that are highly reflective to radar wavelengths. But for the most part, you can make use of radar transceivers in an awful lot of applications. Now, today, the latest and greatest in radar is actually something called guided wave radar. This is where instead of just a radar horn aimed down into the tank, we actually put a metal rod or a pair of metal rods down into the tank, and we send our radar pulse down those rods. Now, this is really handy because, first of all, it means we can use less energy. It does mean, though, that we have to tap into the tank. So a guided radar system is invasive. It's not like a non-invasive where we put the radar horn on the outside of the tank. But the nice thing about guided radar is it gives us a chance to do something interesting. In this particular diagram, I'm showing a tank that has a single fluid in it. But remember, we talked about some cases where we want to find out if there's a bottom level of other fluid, like water accumulated at the bottom of the tank. How do we measure that? Well, with guided radar, when we send the pulse down the guide, generally it's going to be reflected back by the first interface it sees, so the process fluid level. But in many cases, enough of that radar energy will continue down the guide to where it will either hit the bottom of the tank, so we'll have a bottom measurement, or if we have another liquid down there, let's say there's water at the bottom of this tank or something else, when it hits the interface between the blue fluid and whatever's at the bottom of the tank, we'll get another reflection. So quite often with guided radar systems, we can actually not just determine the level of the primary fluid in the tank, but we can also detect the bottom. Remember, we talked about using the displacer for this before. Well, guided radar systems will give us the same kind of capability of measuring both the bottoms as well as the overall fluid level in the tank. So again, they can be used in a lot of applications, and they're very precise and, quite frankly, very less prone to errors from reflections and other things because it is a guided radar scheme. We can also use radiation. In some applications, and a good example of that would be in a refinery, in some of the distillation columns and certainly the coking units, we're dealing with horrible temperatures and pressures and very caustic materials and stuff that is somewhere between tar and cement in consistency. So most of the measurement types of technologies we've talked about so far would just fail completely. So what has been developed through the years is the use of radiation-based measurement. And what do we mean by this? Well, if I take a radioactive substance, some type of a radio source, it's going to be emitting alpha, beta, gamma rays. I can mount it on the outside of a tank, and at that point, pretty much the alpha and beta are not going to go anywhere because they're not going to make it through a tank. But gamma rays have a pretty good ability to penetrate almost anything. So this radiation source will generate gamma rays out, and sort of pretty much in a not exactly guided manner, but sort of spray them in all directions. If I then on the other side of this vessel or tank mount detectors, and there's a variety of different types of detectors, everything from Geiger-Muller tubes to scintillator devices. But if I place radiation detectors along the side of the tank on the other side, and I measure the signal strength of gamma rays that are striking them, then as the material in the tank raises up in level, it will start blocking the path of the gamma rays between the radiation source and these sensors, and it won't stop the gamma rays in most cases, but it will significantly reduce their strength or intensity. So as the level of the material in the tank rises or drops, by measuring the increase or decrease in the gamma ray activity measured by the different sensors up and down along the side of the vessel, I can actually get a rough idea of the level of the material in the tank. Again, this is, there's a variety of different techniques used. Sometimes we use a single point source like this shows. Sometimes we use a strip source. And of course, there's a whole lot of regulations and safety things involved anytime you're making use of radioactive materials and certainly control of radioactive substances. But in some applications, there's just really no other way to make a measurement, and it turns out that the use of radioactive sources is about the only thing we've got that we can use to make those measurements. So I guess we should be lucky we have them. Now, there are other times we want to make measurements in materials that are not liquid. Maybe we're trying to fill a vessel with sand or grain or pebbles or, crushed aggregate. This stuff doesn't tend to level out and give me a nice flat surface like a liquid would. It's going to pile up in a bin. And in many cases, I don't really care about the exact level. What I care about is whether the material in the bin has dropped down to a certain point where I need to make sure to go fill it again, or whether we've gone up to a certain point where we can't put any more in it. So sometimes all I really care about in a bin situation is point level measurement. In other words, is the level below here, is the level above there? And in this particular case, we're showing a type of device called a rotating paddle transmitter. This is actually something where you cut a hole in the tank and you stick the paddle in and you bolt the whole thing up. And this motor drive here turns this paddle slowly. Now, if the paddle is hanging there in air, it's going to keep turning. If you keep pouring stuff into the bin and it builds up and up and up to where it finally covers the paddle is on a slip torque system, so the paddle will stop turning, and the motor that's driving it will notice a increase in torque. In other words, the thing's not turning, the shaft's being held, and that increase in torque will be usable as an indicator that the level has at least reached this paddle. So in the example we're showing here, we've got a bin where we've got a paddle at the bottom of the bin, at our low point, we've got a paddle at the high point, and we've got a fail-safe paddle sticking in from the top. So what does that mean? It means that I can determine if the material level in the bin drops below the low level, because then the paddle there is uncovered. I can tell if the material in the tank is above the high level. Why? Because the high level thing isn't turning. And I can tell if we've gone too high up in the tank because the fail-safe paddle stops turning. So I don't have an exact level measurement. All I've got is an indication that I'm at the bottom or top or way too high in the tank. So sometimes point measurements are perfectly adequate. And if point measurements are adequate, there are many different techniques can be used. Let's go back again to the case of fluids. If I need point measurements in a tank, up and down the tank for a fluid, I could use the paddle scheme. It would work, but, you know, rotating mechanical devices have a variety of different problems, and we don't want leaks, especially if the thing is pressurized. So instead, I might use something called an RTD thermal switch. And an RTD thermal switch is a device where there's three little metal probes. One has a heater in it, and we've got a probe that is heated and a probe that is unheated. The heated probe is being kept to roughly the same temperature as the heater itself. The heater is physically isolated from the unheated probe by a small distance. Now, if this whole probe is sitting here in air or gas, whatever, air or other gases do not have enough thermal conduction to carry heat from the heater to the unheated probe and bring it up to the same temperature as the heated probe. On the other hand, once this probe is submerged in liquid, and the liquid will act as a reasonably good conductor of heat, and we'll start noticing the unheated probe's temperature will rise because it's being heated by the heater. And if we wire this into a Wheatstone bridge, we can make a temperature measurement calculation here, and we can determine that, in fact, the fluid level in the tank has apparently now risen to and is at least or above the point of this probe. So if we put several of these probes into a tank, we can tell as the fluid level reaches and goes above or drops below any of these probes by the change in resistance. Again, these are point measurement devices. So here we're kind of showing that. So I could put one of these up at the top end of the tank where we don't want to go above, and something down at the bottom level of the tank where we don't want to go below, and give me 2 point measurements that are essentially just an indication that says fluid level is below this point or fluid level is above this point. And if I don't care about the absolute level in the tank, just making sure it doesn't go below the low or doesn't go below the high, then these 2 sensors would be adequate. And again, these are point sensors, so they're really generating a contact signal, not an analog signal. They're not continuous reading. It's contact that says, yes, the fluid level's at this level or above, or no, it's got to be below me. Okay? The last way we'll talk about today to measure level is another inferential way of measuring level. I think we pretty much would all agree that if we take a tank and we start filling it with any fluid, as the level in the tank goes up and up and up, because we're putting more and more fluid into it, the tank's going to weigh more, right? So as I fill a tank, its weight's going to go up. Well, if I take a tank and set it onto a set of load cells so that the legs that support the tank, and here we're showing 3 legs, if we take this tank and we set it on a set of load cells, and these are devices that as you press down on them harder and harder, their resistance changes, and we can measure their resistance, and by that we can tell how hard you're pressing on them. Well, we've already said that a column of fluid exerts a downward pressure or force, so as the liquid level in this tank goes up, and if we know the density of the liquid in this tank, and we know what the starting weight of the tank is empty, then we can make a measurement of the downward pressure being exerted onto these load cells at the bottom as the fluid level goes up in the tank, and use that to make a rough calculation of the level in the tank. Now, again, there are certain issues here. You need to make sure that the tank is very properly balanced. You don't want it to be leaning one way or the other because it has to sit exactly on these load cells. So I've seen applications where you've got a tank and the wind is blowing and pressing against the side of the tank, which actually causes the level indication of the tank to change because the tank is now sort of pushing one way, so it's taking the weight off one of the legs and putting more weight on another leg. So you have to deal with things like that. As I said, the tank has to be absolutely leveled appropriately, but this is a technique that's used in a lot of different applications. So we can make a level measurement inferentially by making a measurement of the pressure or the force pushed downwards by the tank as the fluid level in the tank increases. So we can make a level measurement by the basis of the weight of the tank measured using things like load cells. All right, what are the good and bad things about using load cells? Well, they are non-intrusive. We don't have to stick anything in the tank, so if the tank is full of something that's terribly corrosive or nasty or pressurized, we don't care. It certainly works fine for liquids, granulars, and slurries. Now, it doesn't care what's in the tank. You want to fill the tank with puppies, you want to fill the tank with Kool-Aid, the weight will go up and we can measure it. It has a pretty good accuracy overall. But again, it's something that really is hard to add on later. It's usually, if you're going to use this approach, then before you order a vessel and manufacture and have it put in place, you really want it there. Again, it usually requires some kind of either a freestanding or free-hanging structure. You can't put a load cell on something that's already mounted in place. It's got to be sitting on the load cell. So the structure has to be freestanding, and then that means that the structure better not be affected by outside forces. So if it's a tank outside, wind loading will affect it. If it gets covered with snow or ice or just wetted down by rain, that will affect its measurement. Now again, it's an overall weight measurement, so therefore if you have something in the tank like a fluid whose density will change over temperature, well, then we're not really measuring the level in the tank. So if stuff in the tank gets hotter and therefore expands, we're not going to see a difference because the weight hasn't changed. So in some cases when we're using this type of measurement scheme, we have to use temperature compensation to correct for that. But it can be used in a lot of different applications, continuous process control for the storage of liquids, granular slurry. So this is something that you will see out there. It is used. All right, so we're at the end of the third section. So what did we talk about? We're discussing electrical means and electrical technologies for measuring level. We talked about electrical devices that change capacity or conductivity or resistance. We talked about the use of active devices like ultrasonic and radar sensors that send out pulses and time them coming back. We talked about mechanical devices, electromechanical devices like thermal sensing and rotating paddle. We mentioned resistance tape. We discussed nuclear measurement device, the measurement of gamma rays as a way of identifying the rough level in the tank. And the last thing we just talked about is the use of weight measurement through the use of things like load cells as a way of indirectly making a weight measurement. All right, so that's the end of our slides. Let me turn it over again to you, Rashira, for questions.
Again, press star 1 on your telephone keypad to ask a question. If there are no callers on the line, the operator will announce your name and affiliation to the audience and then ask for your question. If other participants are asking questions, you will be placed into a queue until you are first in line. While in queue, you will be on a listen-only mode until the operator indicates that your phone has been activated. The operator will announce your name and affiliation and then ask for your question. Again, if you would like to ask a question, press star, then the number 1 on your telephone keypad. And there are no questions at this time.
All right, thanks very much. Well, in that case, let's take us to the end. One of the things we would like to ask all of you is to answer a quick poll. We'd like to get an idea of the number of people at your site. We know how many sites are dialed in, but we'd like to know how many people. Just something we use for statistical purposes. So if you would, please, well, we've got this up. go to your web browser and click on the appropriate number to give us a rough idea of how many people are at your site. I'll give you a second or two to do this. All right, I guess we've got everybody. So let's go back and finish up our slide presentation. And we'll at least try to finish up our slide presentation. All right, back we go. All right, so thank you for letting us know. So again, we're glad that you could join us today, and we hope you're enjoying this course. The ISA takes training very seriously, and if you are finding this course useful, we'd like to mention to you that the ISA has several related courses. If you'd like to have a week spent playing with instruments and controls and learning how to tune loops and such, please think about attending FGO7. We also have TCO5, which is specific on tuning control loops. And also, if you're interested in becoming a certified technician, the TS00 course is going to help you review and prepare for that course and that certification. If you're interested, please contact the ISA. In addition to those courses, if we get the slide to change, down slide. In addition to that, the ISA offers a couple of different certifications. It would be useful in your career path to become a certified automation professional, a CAP, or a certified control system technician, CCST. The ISA offers both these two certifications as well as training programs to help prepare you for those certification tests. Again, if you're interested, please contact the ISA. Last point today, we are going to be sending you the Zoomerang survey. The ISA takes these courses very seriously. We're constantly looking for feedback so that we can improve them, add to their content, and make sure that they're relevant to you. So please, when you get this survey, we would ask you to fill it out and send it back to us. And at that point, Rashir, let me turn it back to you and finish.
This concludes today's ISA web seminar. Please do not forget to fill out the evaluation survey found in your email inbox. Thank you for attending. Have a great day.